May we now call upon Dr. Prabodh Vajpayee, once again from the August Institute, Department of Electrical Engineering of IIT.
Very good afternoon to all of you. It's my pleasure to be here and to interact with you. And it's always a tough job for the speakers after the post-lunch session to keep the audience awake and listening them carefully. And I'm seeing that audience have taken their own comfort zone where after the post-lunch and they are taking comfort in their zone. And as Professor Das has already taken you deep in the bioenergy side, I will take you out of that and bring you on the general platform of smart grid. And again, I take the advantage of the previous technical session. Professor Chanda in the previous session has already touched about the smart grid, and he has put a question mark over that whether it should be smart or intelligent. And so moving forward on that, I think that we are already smart enough, our grid is already smart enough, and we need a smarter grid. So we need to add some more things which make our grid or make our electrical system more smarter. So this presentation has some outline. So I will take you in deep on smart grid, so the different definitions, different aspects, different applications, different domains of smart grid, how does it take care of. And then in Indian context, how does this smart grid is relevant, what is the need of smart grid, and how does the policies and targets make us forward on that. So there is a roadmap already prepared, which we have already started moving on that, and we will see the roadmap for India in a smart grid context. So as we already know that our electrical power industry is not very old, it's hardly 120 years old, and but it is the greatest engineering achievement till date, and it's unfortunately most polluted industry also, because even 40% of carbon emission comes from the electrical power generation. And in our Indian context, as we know, we have total installed capacity of 275 gigawatt. Out of that, hardly 13%, that is 35 gigawatt, is from the renewable energy generation. So if you have that 40% from total electricity generation, and out of that, this 13% from the renewable generation, so we are only mitigating 4 to 5% of carbon emission through renewable energy generation till now. Our potential is still 1/4 exploited. We have still left with 3/4 of our renewable energy potential to be exploited. So we have different needs. So developing countries seek to improve it. The electrical grid is required some improvement in the terms of expansion, because still 1/4 of our households are not electrified. So we need the expansion. However, in the developed countries, it needs to improve. Improve means the services need to be improved, the quality is to be improved, and there are many new issues are coming up, like electrical vehicle and integration of renewable sources. So there is a need, or there is a thrust on transition to smarter grid, and that is because of the force on climate change to need to incorporate or to include more and more renewable energy sources. But there is a major technical problem with the renewable energy sources is of their intermittent nature of power output. So to handle or to take care of that intermittent nature of those sources, one of the major rollback, one of the block in the development of smart grids. Then another objective is to provide more choice for the power quality to the consumers. As well as we are increasing in demand, peak demand is growing higher and higher, and increased deregulation that has already been touched in the previous session, that how the restructuring in the power industry is making competition, and the electric vehicles. So as our electrical mobility program has already targeted for 6 million electric vehicles by 2030, so that is also one of the major challenge. So we are moving from traditional electric grid to the smarter grid, and that another important component required to add on is the automation through the communication and information system. So that has to be an additional layer of that ICT sector, which has been already mentioned in the previous session also. So the important integration of communication and infrastructures, information technology infrastructure is required with this electrical power grid. So there are some issues with our conventional power system, like the major issue is about the gradual depletion of the fossil fuels, the power energy efficiency and environmental pollution because of those fossil fuels. So we have some energy policy which are developing with the aim of electrical energy supplies with decarbonized or low carbon sources. So that will reduce the greenhouse gases, that will mitigate the climate change as well. And as well as secure and non-dependent on imported fossil fuels. So that will reduce our dependence on fossil fuels which are imported also. So it will improve our economic and affordability by the industry and commerce and all sections of the society as well. So to meet these objectives, so we need to improve the distributed generators or distributed energy resources and renewables and cogeneration in our existing grid. Now the question is, how do we define the smart grid or a smarter grid? So smart grid does not have a unique definition. As much literature you will go through, you will find the bigger and expanded form of smart grid definition. So there is no standard, there is no unique definition of smart grid exists. But it incorporates a lot of various aspects, like it has flexible, secure, cost-effective, decarbonized power system. So a lot of fancy and new words are incoming. And it also incorporates the modern information and communication technologies. It has intelligently controlled active networks that facilitate integration of DG. So our current distribution network is called unilateral passive network because the flow of power is from transmission to distribution to load. So it is unilateral as well as passive in nature because there is no source involved in the existing distribution grid. It's only the load is there. So it has to be transformed into bilateral and active distribution grid where the power flow will maybe from distribution to the transmission as well as there will be some active sources will be connected directly to the distribution grid. So that will make it bilateral as well as active in nature. Another important aspect is that DSM, demand side management or demand side participation with controllable loads like electric vehicles, thermal storage or electric vehicles, pump storage. So this is a very important aspect to have grid in a smarter way. Intelligently integrate the action of all users. Now the users are not only the producers or consumers. They may be combined. They may be that the new term is called prosumers. So those who produce as well as consume. Like in the previous session, the VESCOM has presented about the rooftop PV system. So as a whole, as a residential house, you will generate the PV from your rooftop as well as you will consume from the grid. So when your PV is not enough, you will be importing the power from the grid, and when your load is not enough, you will be exporting the power to the grid. So you will become prosumer. You will not no more as a consumer at all. So efficiently deliver the sustainable, economic and secure electricity supply. There is another definition given by one of the non-profit R&D organization of USA, that is Electric Power Research Institute, and it says again a very broad definition of smart grid. The power system made up of numerous automated transmission and distributed systems, all operating in a coordinated, efficient and reliable manner. So the coordination and the real-time monitoring and signaling is very important in this aspect. The power system that handles the emergency condition with self-healing action in response to energy market and utility needs. So that we need to make it more reliable, more resilient. So as soon as there is an emergency, there is a cascade failure, the grid needs self-healing. It should take care of the faulted part as away from the normal part, the healthy part, so that the rest of the network remain healthy and it should restart or restore as soon as possible. The power system that serves millions of customers has an intelligent communication infrastructure enabling timely, secure and adaptable information flow needed to provide over the evolving digital economy. So once your advanced meter will come to your home, you will be able to communicate with your utility also. Till the time, there are some smart meters have come, but still they are unidirectional. The utility can communicate with the customer, but customer cannot communicate with the utility. So once the two-way communication will be there through this meter, because that is the interface between you and utility. So that interface will provide you two-way communication as well. So this is a general kind of overview of a smart grid where you can see all the building rooftops are placed with the solar rooftop panels. There are wind energy plants are also there, as well as there are conventional power generation sources also. And there are some storage are shown also in the form of batteries as well as the hydrogen. And they all are connected. The main important aspect is they all are connected with this green channel. So that is the most important aspect, that monitoring and the control has to be near to the real time, and for that you need to observe the system on a global basis, and that's one of the important aspects of the smart grid. So these are the key application areas of smart grid, where you can see that it's related to electrical distribution. As I told you, the electrical distribution will no more be unilateral and passive, it will become bilateral and active. Renewable energy is coming in a big way. Storage is an important aspect to make it more reliable, because intermittent nature of your output of the renewable sources also makes compulsory the storage to bring in. So like in the previous session, the BESCOM was showing the grid interface inverter, but they shown at the end also the hybrid inverters. Hybrid inverter means you will have the battery also. So otherwise, suppose you are generating the PV, right, and you don't have grid is not available at that time. Even if your PV is available, you will not able to use your PV. So you have, or you must have the storage at your on-site also. So even if one grid is not there, you can utilize the PV power output. If there is no storage, even if grid is not there, your PV is useless. So in that sense, the storage is very important. Transportation is going to a big way in electrical way. So electrical mobility is coming up in a faster way. Industrial energy efficiency, lot of new certificates kind of mechanism, market mechanism are coming up, like renewable energy certificates are there. Building energy efficiency, we are talking about the zero carbon or zero emission buildings, where the net import from the grid is of electricity is zero. Electricity markets providing all these platform for these kind of activities, and environmental markets, so CDM and all those are the provide those kind of facility. So coming to the smart grid concept, so broadly if we look on few important aspects, it is related to the first is advanced metering infrastructure. So that take care of demand side management as well as energy efficiency. So you can provide the customer, the utility can provide the customer the right moment or right way of planning its load. Okay, so if there is a time of day tariff, so he can optimally plan the load pattern of its own consumption on a daily basis. Or even if he can use the smart energy management devices through which he can remotely control those devices switching on or off, like any kind of home appliances. So those kind of activities are coming in terms of energy and advanced metering infrastructure. Self-healing electrical grid, which is supply the reliability, to improve the reliability, as I told you, that to remove the unhealthy part from the healthy part. And distributed energy resources, which are another important aspect related to the microgrid, because microgrid is a kind of part of the smart grid where the renewable energy sources are directly connected to the distribution grid. Small size, maybe in the range of few kilowatts. And then the bidirectional flow of information and power. So as I've told you, this smart meters will provide you the two-way communication with the utility as well as power flow. So this is an architecture where the communication framework is a very important interface between the control center and the different part of the power system, like generation, transmission and distribution, and along with the load. So if you compare with the current grid and what we are talking about, the smart grid, on different aspects like system communication, so in present it is limited with the power companies and it needs to be expanded and it needs to be real time. Real time is close to real time, not exactly real time, but very close to the real time. And interaction with the energy users, it is still limited to the large energy users, so it has to be extensive and two-way communication is required. Operation maintenance, generation is at present we have mostly the centralized generation, which will become distributed as well. Centralized will still be there, but more distributed generation will also come. Power flow will be more extensive, it will be more reliable, as well as topology of the network will become more network type, no more radial in nature. So going in back to the domains of important aspects like advanced metering infrastructure, so it provides two-way communication is the most important aspect, as well as real-time pricing, direct load control, load monitoring, and these are the remote home control. These are the major aspects which are important with respect to the advanced metering infrastructure. I think I have enough time? No. So, coming to the distributed generation, as I told you, the microgrids are one of the major important component in the smart grid, which provides the low power renewable energy sources directly connected to the distribution grid. And the wide area measurement and control system. So it provides you, the wide area means the whole monitoring of the whole system all together at one place in real time, close to the near real time. That's why it is called the wide area measurement, as well as you provide the control to the system also. These are the real issues which we are handling in our institute on these aspects. So relevance to the smart grid in India has already been discussed, and if we compare it with the three different segments of economic, service and environment, so all have their own reasons to justify the need of smart grid in India. And so it will reduce the cost, it will reduce the operational maintenance cost. Industrial China has 4,000 kilowatt hour. So we have to go a long way, and there is definitely, we have to work very hard for that.
Okay, thank you.
Sir,
Any more questions?
Sir, microgrid need to be connected with the grid, or it will directly supply to the distribution system?
See, as per the microgrid definition, again there are multiple definitions exist, but mostly the in a broad way, the microgrid is limited to few kilowatts, not of megawatt scale. So in that sense, it has to be connected to the distribution grid, right? But it may go up to 132 kilowatt also.
And no need to connect to the grid, and it may distribute to the distributor.
Yeah, it may be in off-grid mode also, it may be grid-connected mode also. So standalone mode is also a microgrid, and grid-connected mode may be also a microgrid. So microgrid has a facility to island from the main grid as well as to grid-connected mode also.
Okay, thank you.
Thank you so much. Thank you.
How do you envisage the double connection? I mean, from consumer to generator?
Pardon?
How do we envisage the double-way connection?
Actually, what I mean to say, how it can be possible that a consumer is supplying power to the grid? Is there any technical feasibility here?
What is the problem in supplying to the grid? What do you mean by that?
Actually, it's a double connection, I think.
Yeah. So how the power flow? What is the basic physics behind the power flow?
So it's the voltage.
Yes. So if you generate the voltage at higher voltage, generate the power from PV at higher voltage, you can supply it.
Okay, thank you.
Thank you so much. And as we bid goodbye to Dr. Das and Dr. Vajpayee, may we call upon Professor Dr. P.K. Sadhu for his presentation.
I also thank the organizers for organizing such a wonderful seminar on renewable energy sources, as because this is becoming one of the major thrust area in the energy environment. Okay. Now we are in this session actually trying to know something about wind, right? Harnessing power from wind energy, and then how to utilize it, the Indian scenario, the global scenario, and the basic technologies. Okay. Now, as regards the history of wind turbines, it is a very old kind of thing. People used from even 2000 BC, where they used wind turbine mostly to grind some certain grains, food grains. Okay, and then the first commercial wind turbine actually came in the late 19th century, that is 1888, where actually it was developed in USA, and from 1980s and onwards, actually the modernization on this wind turbine technologies along with different energy recovery, electrical developments and all that came into picture. Now, the ancient windmill structure was like this actually. As we see, it was in 2200 BC. Now, if we look at the energy scenario these days, from 2013 to a projection of 2030, amongst all the non-conventional sources, if we see this wind and solar, they're growing actually side by side. Nowadays, even wind is slightly more than the solar, but the projection of 2030 is it will even overgrow from the solar power generations. This wind and then wind offshore and onshore. Okay. Now, if we look at again the global scenario regarding the country-wise power generation from the non-conventional sources, India is actually standing here. Actually, there is no pointer. Actually, the second from the top. Actually, the second from the top. If you kindly see the color combination, and that is also growing up from 2008 to a projection of 2016. And as on date, actually, India makes wind production 1/3 of China around, 1/4 of Spain, and even lesser from Germany or US. But at least the you can say that growth in Indian scenario is coming. And this is the generated wind power these days in 2015 around 20,000 megawatt. So now, what is the wind energy actually? Now, we are thinking, we are studying a lot about renewable energy sources, and if we look at all the renewable energy sources are coming from the sun, except the tidal and geothermal power. And the earth actually receives around this many of 1.74 into 10 power 17 watts of power per hour from sun. And out of which, if we look at, around 2% of this energy is converted directly to wind energy, and which is very, very huge, which is about even 50 to 100 times more than the energy converted through biomass by all plants on Earth. Therefore, if we see that the prospectability of wind energy conversion system is quite large if we look at the generation from the non-conventional sources. And how wind comes, it is well known, this land-sea cycle. It is actually differential heating of Earth's surface that causes wind to blow both in vertical and in horizontal direction, and that is utilized to generate power after rotating turbines. And turbines are coupled to generators, and then the generators will be generating the power. Now, comparison with other energy sources, if we look at regarding wind energy, it is more environmental friendly. That means it has got less hazard compared to other non-conventional sources. And there is a large resource of supply, as already talked about, that the resource of supply is a very large. And then the operating cost is also very cheap. It is around 1 cent per unit of energy. So once the thing is installed, rather once the plant is installed, the operating cost is almost maintaining the wind plants. Rest is very common. Now, if we look at the wind turbine types, now there are various turbines that can be actually constructed or even mounted. And there could be more small and some larger turbines also. So there are choices between small and large turbines. And sometimes we prefer for some sites to be constructed with larger turbines, because it can able to deliver more power, and the foundation costs and all, if we accumulate, say supposing a 5 megawatt turbine if we want to construct, and then make 500 kilowatt into 10, and total installation cost of 500 kilowatt into 10 will be more. So therefore, total installation cost-wise, it will be economic. And usually, the large turbines, they are suited for offshore plants actually. Offshore plants, if someone has visited the Western countries like Sweden, Norway or Germany, and you will find that lot of wind turbines, they are actually mounted offshore in the sea. And then, in the areas where it is difficult to find multiple sites, like wind turbines, the turbines have to be constructed and they have to be mounted on a particular site, and all the soil things has to come. And then if we see that there is not large area where we can just install those turbines, one single turbine will do. So there also it will be preferred. And sometimes small turbines are preferred, where actually we see that we have enough space, as well as a single turbine problem is that in wind there is a lot of fluctuation of power. Wind flow, as we see, it is not uniform throughout the day, or you can say throughout the year, throughout the month, like that. So once it is installed, then there can be a fluctuation of power. And if the wind turbine is large in nature and it is feeding a grid, then that fluctuation may affect the grid. And therefore, it can be split up into small turbines if possible, and then failure of even one turbine doesn't interrupt the entire power. So that is also another consideration for actually important for generation of power. And one term is defined as tip speed ratio, which is actually omega r by V1. Omega r is actually the linear velocity of the wind blades, and V1 is the turbine blades, and V1 is the wind speed. And this lambda ultimately is related to power generation is like this: Cp into P in, and Cp is directly related to lambda, and the variation of Cp with lambda is given by these graphs actually, where we find that if lambda increases, that means the tip speed ratio is increasing. That means to wind velocity, the turbine speed is increasing, and the plot is like this for different angles, different pitch angles. Pitch angles are the angles of the turbine blades. That means how it will interrupt the wind. So that turbine blade is a pitch, theta is the pitch angle ratio. And then it is related, the developed power is related by half Cp into rho into At into V1 cube, where rho is the air density, At is the swept area, actually area covered by the turbine blades, and V1 cube is the actually velocity cube. Now again coming back to generated torque, actually as we see that here the torque will be input to the machine, and ultimately we will have a generation of electricity, a positive power generation. And then the generated torque versus generated speed is given by these curved lines. And we will want to operate at a point where the generated torque is maximum. That is known as the maximum power point tracking system. Actually, all the wind turbines will be designed to operate at a best maximum power extraction, where we can have maximum power output from the turbines, rather maximum torque outputs from the turbine, and that will be generating electrical power as a prime mover to the generators. And then we have, for that actually we have a particular cut-in speed below which the turbine does not rotate or does not have, does not rotate you can say, above which it will start rotation or start producing power. And the cut-in speed depends on turbine to turbine design. It can be around say 8 to 9 kilometers per hour, and the average cut-in speed is 10 kilometers per hour, and the best, the average speed of generation, better generation is around 12 kilometers per hour. 12 kilometers per hour. And these are the construction of turbines. Basic two types, horizontal axis and vertical axis. Till now, vortex turbines are also coming. So horizontal axis turbines looks like this, where we have a horizontal wind blowing, and then the turbine blades rotate. And this is most common design today. And that your direction, actually I don't have a pointer, I could have shown it in a better way. Actually there will be two motions. One is the blade motions that is rotating, and then this one, what we saw that the pitch angle rotation. That means the blade has to interrupt wind, the pitch angle, and the third is the yaw rotation. All those things will combine to extract the best power, or rather the maximum power from the wind turbine. And this is the construction of the vertical axis turbine. There actually the main advantage is that it can generate power from any direction of wind, and the generator is mounted at the bottom through suitable gear arrangement and utilizes wind flow in all directions. Advantages, disadvantages are not of major nature, and these are the concerning things. Now a typical 600 kilowatt wind turbine will have a rotor diameter of 43 to 44 meters. That means its mounting you can say height will be at least 70 to 80 meters, 70 meters around. So then the turbine diameter actually increases. This is the graph actually showing. For a 225 kilowatt generator, we have 27 meter of you can say swept area turbine diameter, and then it is increasing as a square. as the power generation is increasing as a square of the diameter of the wind blades. So that means 4 times energy will produce if we increase the diameter 2 times. So that is one. And for a typical 2,500 kilowatt wind turbine, we have 80 meter of dia for the wind blades. Now, this is the actual thing which I am trying to talk about. I am not expert on those things like turbines. Now, electrical side, wind turbine generators. Now, wind turbine generators, if we look at, there are 2 basic type of generators. One is induction generator, then another is synchronous generator or alternators. Now, induction generator, large and small is okay. This is the basic type of control. For induction generators, there are certain advantages. Like, it is, if we are using a squirrel cage type of machine, it is very robust. That means we require very less maintenance. And also, we don't require any DC supply, right? As we require for, you can say, a synchronous generator or other type of induction generator. The other type of induction generator used is doubly-fed induction generators, which are actually the slip ring machines. Slip ring machines, they are also handicapped by maintenance of the slip rings. Not only that, the rotor power has to be suitably controlled in order to have generation from the doubly-fed generators. But another advantage is that for a slip ring machine, for squirrel cage machines, the operating speed range is very less. Operating speed range is around 4% about the synchronous speed. But here, for the doubly-fed induction generators, we can extend the operating range to around plus 20% to minus 20% around the synchronous speed. That means if I have a 1500 RPM induction generator, the squirrel cage type will give you a speed range of around 60 RPM. That means 4% above 1500. And for a doubly-fed induction generator, you have 20% of 1500. That means 300 plus and 300 minus in both sides. So 600 variation of speed, 600 RPM variation of speed can be achieved. Now, this is the basic control topology where we have wind, pitch control, yaw control, and ultimately this is a gearing, and this EG is the actually generator, electrical generator, and that is controlled from the voltage control, power control, etc. will come into picture. This is the basic control diagram for the system, and this is the view for the squirrel cage type of generator. Now here we will discuss a little more. Like here is a system where we have used a back-to-back converter. Means here the speed range can be widened simply because it can generate from a lower speed of around, so I'm taking the example of even 1500 RPM induction generator. So it can start generation from about 900 to 1000 RPM. But the frequency will be less if we have a standalone system. But here, as we have connected the systems to a back-to-back converter, now here we can have a frequency which is as per the rotational speed. That means from 900 RPM it can generate around say 30 Hz or something, and then it is converted to DC and then converted to back to AC at a suitable frequency, that is 50 Hz as per the utility connection, and then that is stepped up. If the voltage level is less, then it will be stepped up to the transformer and connected to the grid. So other connections are also possible for standalone generator where we don't have this system. Only we have a synchronous induction generator connected to capacitors to supply the reactive power during generation, and then the variable frequency supply can be converted to DC and finally to AC. This same back-to-back conversion system, and then it is feeding directly to the load or to the grid system. The other thing is that DFIG system, double-fed induction generator, where we have actually slip ring type of connection. Like what it does actually, now in the stator, if we see, it is directly connected to grid, and the rotor is actually connected to grid via a transformer and back-to-back converter. This back-to-back converter has a very important role for generation. the first one, the left side one, is known as the rotor side converter or RSC. So the right one actually is known as the grid side converter or GSC. The grid side converter is actually meant for making the DC voltage constant at the DC bus level. Okay? And the rotor side converter is actually used to control the active and reactive power supplied by the stator. And if we look at the subsynchronous operation, as I was talking about, that this type of structure or this type of generation can generate power from 20% of rated speed, 20% of synchronous speed below. That means from 1200 RPM to 1800 RPM. So below synchronous speed, actually the rotor will receive power from the grid. So net output power is actually generated stator power minus the power received by the rotor from the grid. And in supersynchronous operation, if we see that the stator will also provide power to the grid and the rotor will also provide power to the grid through slip rings. Now the transformer is actually for stepping up the supply to the grid system. Now this is the configuration of back-to-back converters practically. Now this has been taken care of. The other actually, now this concludes the induction generator principle. The other one is the synchronous motor, synchronous generator actually. So synchronous generator, as we see, actually it can generate power right from the turbine rotation. Although the frequency will vary, if the turbine rotates, it will generate power, although at a lower frequency and a lower voltage. So what we need to do is that if we want to connect it to a grid, we have to convert it to a suitable frequency which is equal to the grid frequency and also at a suitable voltage. That means equal voltage, you can say, to the grid at a leading power factor angle, so that the power flows from the generator side to the grid side. And now here we have two supplies actually. One is a DC exciter, which we need for the rotor, and nowadays even from some small permanent magnet synchronous generators are also coming into picture, so that the DC supply is avoided actually. It can directly generate power from the permanent magnet generator. But here actually what is done, a part of the power developed, power generated by the generator is fed to the rotor system. But initialization will be required. So initially we might need some battery so as to start up. And then once it has started up, actually the generated power can be directly connected to the rotor supply. And then this converter system, the second rectifier and converter, is actually converting the power to the required frequency and required voltage level. Now, as we have already started and our previous speakers have also explained that wind power or this non-conventional powers, especially wind or solar, they cannot be available throughout the day at the same rate. So therefore, actually, in order to have a grid independent from the, you can say, the conventional grid system, made a grid which is, say, a microgrid, made up of the non-conventional sources, primarily from solar or wind. So the hybrid system is can be planned along with the battery backup. Although the battery backup is very limited because of the several disadvantages of batteries, but wind solar hybrid generating schemes are also available these days, where integration can be done both at grid level as well as at the generator level. In the grid level, actually, the power generated from the wind and from the solar or other sources, they are brought at the same grid and then connected through suitable converters with the help of proper connection. And the other one is generation level, that is the generation itself is comprising of the two different type of sources. So this is the kind of thing that can be done actually, where the rotor side converter is actually not fed from the grid. It is fed from a suitable solar panel along with a battery storage. And then this thing actually works, this can be worked, this thing can work actually even independent of the grid. How? Now when there is a wind, so wind power can be supplied to the load, and when there is less wind, so the solar power can be used to supplement the wind power to generate constant power at the stator terminals. and this can be connected even to grid system. So this is our, you can say, what we are doing at present in Jadavpur University. What we are trying to do is this thing, where we are planning to have a rotor converter supplied from the solar panel, and then the stator converter is connected to the grid, so that we have two types of generation. Like when the speed is subsynchronous, actually the solar power will be supplying the rotor side, and then the stator will generate power to the grid system. And even at zero wind speed, this induction generator, you can say, can work as a direct transformer, so that the solar power can be directly converted to the grid system with the help of suitable frequency conversion at the rotor side converter. And the problem is at super synchronous speed, where actually the stator will generate as well as rotor power is also fed to the system. When in super synchronous mode, we have to arrange either some dumping, either some load which can dump the power, or we can actually connect it to some extra load which is usable, like battery charging, etc., etc. So that's the main bottleneck. Otherwise, it has been true, and the rest things I'm cutting it short. Induction generator. So now some striking factors about wind energy potential in India. Actually, the previous speakers have also emphasized on the same fact that India is also having a very good potential on wind power generation, especially on coastal areas like the west coast, Gujarat, and then the southern coast, Andhra, and even we have West Bengal, 24 Parganas south coast, which might actually give us some amount of wind power, as because the coastal wind is high, although it is not tried still these days. And it has been studied that even at this stage, that in order to generate certain jobs also, the power sector, as we are emphasizing these days that next 10 years, a lot of power plants, a lot of non-conventional sources are coming into picture. So it has been studied worldwide that 1 billion kilowatt hour of annual wind energy generation will create about 500 to 1,000 jobs. So that some people can be employed, even the electrical engineers. That's the good news for the electrical engineers. But one thing that has not been touched upon is that what is the effect of wind power in the environment. If we see that we are trying to reduce all carbon footprints from all the generating systems these days, and wind is one of them leading, you can say. But on the other hand, wind have certain disadvantages also. Like, it generates noise. It has been found that if as a typical 600 kilowatt generator, within 300 meter, we have experienced a noise problem. So the closest neighborhood for this generator should be beyond 300 meter distance, which is of course, although safe, because the wind plants are generated way outside, even the coastal areas and all. And the other thing is that birds and all, they can collide with high voltage overhead lines. Oh, sorry. Actually, if we see that the birds and all, they collide high voltage overhead line poles, and they are also killed by the car. No, actually, wind towers, what we mean to say, wind towers doesn't affect the environment like killing birds or all. As because even you will see that the birds can be killed, even they sit on a transmission line if they touch two wires. But there is less chance in this kind of generation, and that's all I wanted to say. Thank you.
Thank you so much.